So first of all, I'm collecting homework assignments today, so before the end of class this afternoon, that'll be fine. This is the next homework assignment, so that I want back by March 14th. So there's one last problem from Chapter 3 and a couple of new problems in Chapter 4. So today we are getting started in Chapter 4, so we're going to be talking about the Lagrangian and Hamiltonian formulations of general relativity, but I'll give you a bit more background on these topics, and we'll start with the Lagrangian formulation of GR. So just to place this in the context of where we want to be, which is to be talking about black holes. Everything that I've been doing pretty much is building up to a set of tools that we're going to be using when we are dealing with black holes. So we've talked about congruences, and the main purpose for that was to talk about eventually the congruence of null generators that defines the event horizon of a black hole. So in order to describe that, we needed to introduce tools associated with congruences, and we've done that first. Then, of course, the black hole, the event horizon of a black hole is a null hypersurface. So if we introduce the tools required to talk about hypersurfaces, in particular null hypersurfaces in the context of event horizons, and we've talked about other things as well, like the extrinsic curvature, because the extrinsic curvature is something that's really important in many aspects of GR. So I took the opportunity of doing that. The reason to talk about the Lagrangian and Hamiltonian formulation, well, again, it's twofold. I think in terms of intrinsic interest, I think it's pretty high. That's something that is very important in GR, mostly, in a formal connection where you try to pin down what is the variational principle associated with GR, but also more generally with field theories in curved space-time. So I think there's a lot going on there that's intrinsically interesting. Once you have a Lagrangian formulation, well, there's a recipe that allows you to get a Hamiltonian formulation. And historically, the Hamiltonian formulation of GR was extremely important. That is often the starting point to formulate a quantum gravity. And there's been various ways of doing Hamiltonian formulations. The one that I'll do is, one of them. But there are certainly lots of variations on that theme, and they tend to be starting points to formulate quantum theories. So in terms of that, I think there's a lot of intrinsic interest for these topics. But the angle for black holes is that once we have a Hamiltonian for a gravitating system, we have a nice, elegant way of defining a mass for a system. And even more than that, we can use the Hamiltonian to define linear momentum. We can use the Hamiltonian to define angular momentum. And those are things that we can import in a study of physical spacetimes, like black hole spacetimes. So something that's, I think, very peculiar, or at least, a departure from what we may be used to in the context of mechanics. When you talk about the Hamiltonian of a mechanical system, the Hamiltonian is always representing the physical energy of the system. It's always the total energy. When you talk about the Hamiltonian of a field theory, and in particular when you talk about the Hamiltonian of GR, there's a lot more information in the Hamiltonian than just energy. You have the energy, but you also have the linear momentum. You also have the angular momentum of the system, all buried inside this Hamiltonian construct that we're going to be looking at. So in curved space-time, it's a very rich structure that we're dealing with when we're dealing with the Hamiltonian. And the immediate benefit for us in the context of black holes is that we can use those notions to formally define what is going to be the total mass energy of a space-time and its total angular momentum. The total linear momentum is not going to be that interesting for us, because we're always going to be working in the rest frame of that black hole. So this is where this fits, and this is where we're going. And so let's get started. So I'm just going to go back to mechanics just to refresh your memory a little bit about how it goes, in mechanics to give a Lagrangian formulation of a mechanical system. I expect that you know this and know it very well, but I just want to start there just to illustrate a few things about how variations work. So if we're starting with a mechanical system, then typically we're given a finite number of degrees of freedom. And here I'll just take 1 degree of freedom just to simplify things. Of course, it generalizes to any number so long as it's a finite number of degrees of freedom. So we have, we have 1 degree of freedom that's going to be represented by a generalized coordinate q, which could be either, a linear position variable, or it could be an angular position variable. It could be any of those things. We have generalized velocities, the time derivative of the generalized coordinate with respect to time, and we're given a Lagrangian function, which is going to be a function of q and q dot. And, in mechanical systems, that's going to be the kinetic energy minus the potential energy. But for our purposes here, we don't have to specify what the Lagrangian is. We just say that it's, a given function of q and q dot. And with that, we calculate the action functional by taking an integral between 2 fixed times of the Lagrangian function with respect to time. And it's a functional as opposed to a function. I think you know the difference, because in order to get the action, what I have to specify is a full function. So I get an action as a function of a full function q of t. You can plug in whatever choice you want for q of t and its derivative inside the Lagrangian. You can evaluate the integral. After all this, you get a number. That number is the result of evaluating the integral for that chosen function of q. And that operation basically defines what a functional is. You have to specify a full function of t in order to get your number. And that's not what a function is. A function would be, you give me a number, I return a number. Here, you give me a function, and I return a number. And that's what a functional stands for. So the action is the starting point of a variational principle. And what we say is that the equations of motion in mechanics are obtained by considering a variation of the action and declaring that around the true path, the true trajectory of the system, the action will be stationary. The action will be, the true path will be an extremum of the action. And the caveat, though, or the restriction that we have on all possible variations is that at the starting point, we have to all start at the same starting point, and all those paths that we consider in the variation also have to end in the same point. So the picture is where we have a plot of q as a function of time. So I'll do it this way. So we start at a given time, and we end at a given time. We start at a given position, and we end at a given position. And then we can consider all paths that link the same endpoint and the same initial point. We consider all possible paths. We evaluate the action for all of them, and we look for an extremum. We look for the true path around which varying the path produces no change to the action to first order in the variation. So this condition is very important. Otherwise, you wouldn't have a well-defined variational principle. You would have to generalize the rules if you didn't want to impose those conditions. So we always impose those conditions in mechanics. The reason why I bring it up, of course, is that when we're dealing with field theory, which is going to be my next step, we're going to have to decide which is the counterpart to that in a field theory context. What conditions do we need to impose to formulate a well-defined variational principle? So the rest of the story is, well, you just go back to the action and you carry out the variation. And the result of this is going to be to end up with the Euler-Lagrange equation. So I can go through that very quickly. If you consider a variation of the action, then you're inside the integral. You don't vary the initial time. You don't vary the final time. So there's no variation of the boundaries, of the boundary limits here. By varying the Lagrangian, that means that you take a partial derivative with respect to q multiplied by the variation in q. And then you take a derivative with respect to q dot, and you take the variation in q dot, which is the same thing as the derivative of the variation delta q. And all of this you integrate over time. And then the usual step is to express this as a total time derivative minus something else, which is going to be the time derivative of the L dq dot that multiplies delta Q. The total time derivative you integrate, so that's integration by parts, obviously. So you end up with a boundary term. And then you end up with the other thing, which is dl dq minus d dt dl dq dot that multiplies delta Q. You get rid of the boundary terms because, well, you've imposed the condition that the variation of the path has to vanish at the initial and starting at the initial point and the end point. So this is 0. And that's why we had to impose those conditions, because otherwise we would be kind of stuck. And here you say that, well, we want the variation to be 0, but we want the variation to be 0 for arbitrary variations around the true path, except for those two final conditions, those two conditions at the boundary points. And if you have an integral here that's supposed to vanish for any choice of a multiplying function like this, well, it doesn't take too much thought to conclude that, well, the integral can only vanish for arbitrary variations if the integrand itself vanishes. And those are the Euler-Lagrange equations, and those are, of course, what gives rise to the equations of motion. So the Euler-Lagrange equation that follow from that is that d dt dl dq dot minus dl dq is 0, and those are the equations of motion. So typically the Lagrangian will be, so the Lagrangian involves q and q dot. So when you take a partial derivative, you still retain a q dot dependence. So the d dt, of course, will produce q dot dot terms, so those are your accelerations. These will be typically functions of q, and you end up with an equation that looks like f equals ma, where f will be coming from the derivative of L with respect to q, and the acceleration terms will be coming from this guy over here. So in the end, you end up with a second-order differential equation for your q. And, well, you get solutions, obviously, by integrating and imposing boundary conditions. So I guess nothing too surprising or unfamiliar here. So the important point is that in the context of mechanics, we have a finite number of degrees of freedom. Here I had one, but I could generalize to a whole bunch. If I had a whole bunch, I would have a whole sum of terms like this. And because my variations are all independent from one another, each term in the sum would have to vanish independently. So I would have one of those equations for each degree of freedom. So that, that's a familiar story. But the important point is that in the context of mechanics, we're dealing with a finite number of degrees of freedom. And we impose this condition at the initial time and the final time. We have a restriction on possible variations. And that would be true for all the variations if we had a larger number of degrees of freedom. When we do this in field theory, now we're dealing with something a bit more delicate, because we're dealing with a system with an infinite number of degrees of freedom. Right? So I have a field configuration that has a value at every point in space-time, and, well, that's an infinite number of degrees of freedom that we're dealing with when we're dealing with a field theory. So what I'll do now is to just switch to that case, and in fact, I'll switch to field theory, but I'll switch directly to curved space-time, because in order to formulate the Lagrangian formulation of a field theory, it really makes no difference whether you're in flat or curved space-time. The procedure is exactly the same. So let's do field theory. So let's do a scalar field theory in curved space-time. And I pick a scalar field because it's simpler. I don't have to deal with vectorial indices or tensorial indices or whatever. But the procedure is basically identical in all cases, so it just simplifies the writing. to do with a scalar field, but you can very easily parallel the whole discussion to deal with a vector field, for example, or to deal with a tensorial field. And we'll do it for GR, obviously, in the next step. Okay. So in that case, well, we're dealing with a field configuration. So the analog of our Q in mechanics is going to be a field configuration. And while Q was depending only on time, here our field configuration will depend on space and time. So I'll call my scalar field, I'll call it, say, psi. And psi depends on all space-time coordinates. And the immediate consideration here is that this is an infinite number of degrees of freedom. In mechanics, I had to consider Q and Q dot. In field theory, I have to consider psi and all possible derivatives, right? So I'm given this, and by differentiation, I'm giving everything else too. I'm giving all the derivatives. So those are basically the configuration variables for our field theory, also depending on space-time positions. In mechanics, I had a Lagrangian. In field theory, I'm going to be given a Lagrangian density. So it's a Lagrangian per unit volume. So I have a curly L notation for that. It's going to depend on the scalar field, and it's going to depend on its first derivatives. In mechanics, so typically this will be, for a given field theory, this is going to be, it's going to be something like kinetic energy minus potential energy. It's something that's going to be a scalar function of things you can build out of the scalar field itself and its derivative. So for example, because we're dealing with a scalar field here, you can build a scalar out of the field by involving the field itself, and typically you'll have terms like psi squared in your Lagrangian density. And because this is a vector, I need to combine it with the metric and another version of itself, so I can form, something like G alpha beta d psi alpha d psi beta as another scalar that I can stick into the Lagrangian and make that a scalar. So typically you'll have, combinations of, so you'll have a combination of this plus terms involving psi. If you only get psi square terms in the Lagrangian, you have a free field theory. If you have higher powers or some potential energy as a function of the scalar field, then you have a nonlinear field theory emerging from that. But the point is that the Lagrangian density is a scalar function of the field configuration and its derivative. In mechanics, I was getting the action functional by integrating the Lagrangian over time. Here we have the same thing, but I have to get the Lagrangian by integrating this over space, and then I get the action by integrating that over time. So basically, to get the action, I take the Lagrangian density and integrate over space-time. So the action functional, this time it's going to be a functional of a space-time scalar function, is going to be an integral over some fixed volume in space-time, some fixed region in space-time, of the Lagrangian density over the invariant volume element. And again, it's a functional because, again, in order to get this number, that is the action, I have to specify the full function of space-time that the scalar field is and its derivative in order to know what the Lagrangian is, in order to know what I'm supposed to be integrating. So for any field configuration, I get a number, and as I vary or as I change the field configuration, the action will change, and you vary the action by varying the field configuration. The important point here is that in the context of mechanics, we were fixing T1 and we were fixing T2. If I want to do the same in field theory and I want to do the same in curved space-time and put everything covariantly, while I could say that what I need to fix is an initial time-like surface and and a final time-like surface, sorry, space-like, initial space-like surface and a final space-like surface, and we can do that, but then you have to, you have to specify what you're going to be doing at the spatial ends of that domain. So bottom line is that it's much better to formulate everything in terms of a closed region of space-time that's going to be arbitrarily selected. So basically, you give me a region of space-time, and our action functional is going to be defined for that region of space-time. And then, you can consider a small region, you can consider a big region, you can consider that region V to be all of space-time if you want, but fundamentally, you just say that the field theory is going to be defined in that finite domain V, and the action functional is going to be involving the field configuration inside that closed domain. So V is a fixed and closed 4D region in space-time. Its boundary, I'm going to denote delta V. I didn't mean closed, I mean finite. 4D region in space-time, and I have an option of taking an infinite limit if I wanted to, but I'm happy to deal with a finite region. And dV is the boundary, and because my region is finite, the boundary is going to be a closed free surface in space-time. So the picture is that we're given some finite domain in space-time. This is a space-time diagram. Time goes this way, and space goes that way. And we pick an arbitrary region V. We have a boundary on it. And I'm assuming, for simplicity, that it's a nice, simply connected domain, and that the boundary is, one closed surface instead of just a whole bunch of broken up surfaces. But, all of this is generalizable. If I'm given two disjoint regions of space-time, I can join them by, digging a channel between them. So you can do all these things, and nothing changes. So we might as well do something a little bit simple. So that's the analog in field theory to what we had to do in mechanics, which was to fix T1 and T2. And our action functional in mechanics was defined in terms of this finite interval, and we don't care what goes on before, we don't care what goes on after. In the same way, when we define the action functional for field theory in space-time, we care about what's going on inside that volume. We really don't care about what's going on outside of that. And which volume I pick is completely arbitrary. In mechanics, we had to be very careful and say that the variation of Q had to vanish at the initial time and the final time. Well, the analog to that in field theory in this context is going to be to make sure that the variation of our field configuration vanishes everywhere on dV. So the major condition here when we start varying things is that the variation of the field has to be 0 on dV. And that's a condition that will allow us to turn the variational principle into a well-defined procedure that will return the analog of the Euler-Lagrange equations for the scalar field, which is going to be basically the scalar wave equation or the scalar field equation for our field psi. Any questions at this point? So we're pretty much following a parallel route, but just generalizing the rules so that they make sense in a field theory context. And the major aspect of this is the need to introduce this finite boundary in space-time and to fix the variation to be 0 on that boundary. Well, the rest of the story is that you just go back to the action and you just carry out the variation the same way we did it in mechanics. So I'll just go through the steps and we'll see what comes out of all this. So we declare that for our true evolution of the field configuration, the action should be an extremum. So we consider arbitrary variations of our field configuration around a true configuration, and we make sure that this variation vanishes on the boundary. So we vary the action in this way. The volume is fixed, so we don't need to consider variations in the surface itself, variations in the volume, so we leave that alone. When we vary the Lagrangian density, well, first we take a derivative with respect to the field itself, and we vary the field. And then we take a derivative of the Lagrangian density with respect to the field derivative, and we vary the field derivative, which is the same thing as differentiating the field variation. The metric is assumed to be fixed, so the space-time metric is not participating in a variation. Of course, when we do GR, that's the thing that's going to be varying, but for now, I'll leave this alone. Well, the next step is exactly the same as what we did before. So here we're going to convert that into a total derivative. So I'm going to rewrite this as a total derivative, but here I have to be a little bit careful. And one thing I could have done is to say that, well, this partial derivative acting on a scalar is exactly the same thing as a covariant derivative. And what I'm going to do is to transfer the covariant derivative on the first term by just writing the whole thing as a total covariant derivative. So this is a vector. And if I want to differentiate that covariantly, of course, I have to use a covariant derivative. So that's why I made the switch here between partial and covariant derivatives. So the total derivative is going to be this, and then the term that's left over is going to be the covariant derivative of that vector that I get by calculating this partial derivative. And this multiplies the field variation.
Can you explain how that works? Was it covariant all along?
This derivative?
The partial derivative, the covariant derivative.
Okay, no, all I said is that, so at the first stage, I just take, I'm differentiating a scalar with respect to its, constituents, right? So here I differentiate with a field, here I differentiate with the field derivative, and here there's no distinction between covariant or partial because I'm acting on a scalar. And here there's no distinction between covariant and partial because I'm also acting on a scalar. Because I'm acting on a scalar, I have the freedom of switching that to a covariant derivative. And if I do that, then I can use the fact that this satisfies all the product rules of differential calculus. And I can write, and then when I want to start transferring derivatives, it's better to use use something covariant because I'm going to be differentiating a vector now. So of course I could do it all at the level of partials, but then at some point I would want to convert to covariant. And I could throw in a few Christoffel terms that would cancel out and do things like that. But, I think it was just easier to do it like that. There's nothing very deep about any of this. Are you satisfied? Yeah, okay. All right. So here we have a total divergence that we're integrating over space-time. And we know from Gauss's theorem that we can transfer that. We can rewrite this as a surface integral. So the total derivative term, like what we did in mechanics, the total derivative term can be integrated out. And this time we get a full surface integral. So the first term we get after accounting for this is going to be a closed integral over the boundary of whatever was inside the divergence. And we multiply this by the volume element or the surface element on that boundary surface. So I'm just using Gauss's theorem to convert the volume integral of a divergence into a surface integral. So we get that for the boundary term, and then what's left over is the rest of the volume integral. And here we get partial L partial psi minus covariant derivative of partial L partial derivative of psi, all of that multiplying the variation in psi. So basically following exactly the same steps, but doing it for a field configuration instead of a mechanical system. The rest of the story is also exactly the same. We've imposed that the variation has to vanish everywhere on the boundary. That allows us to kill the boundary terms. And that's why we had to impose this condition, because otherwise we wouldn't be able to get rid of this and we'd be stuck. And then this integral has to vanish for arbitrary variations around the true path. The only way this can be arranged is for the integrand itself to vanish by itself. So the field equation in this case is coming from the Euler-Lagrange equation in that context of field theory, and it's given by whatever you get for this derivative minus dl d psi equals 0. So you specify the Lagrangian, and then you plug that into the Euler-Lagrange equations, and you get your field equation for your field theory as defined by its Lagrangian. All right. So maybe just a quick example, just to illustrate how it works. So if we want to do a scalar field theory, then we have to come up with a Lagrangian that is a proper scalar function of these ingredients. And as I said before, there's only so many things you can do to involve this into a scalar quantity. And typically you want to keep the Lagrangian, so let me just write it down. So a good candidate for a Lagrangian is going to be this combination of derivatives that combine nicely into a proper scalar quantity. And then I'll just write it as a self-potential energy that involves some function of psi itself. So this would represent the kinetic energy of the system, and this would represent the potential energy of the system. And now you're asking why the minus sign, right? The minus sign is there because of our convention that the metric would have a negative sign in its time entry, right? So when you basically you recognize the kinetic energy term by looking at where the time derivatives are, and those time derivatives should occur with a plus sign in the Lagrangian, and that defines a positive kinetic energy. So GTT here being negative, I need this negative sign to convert this into something that will have, the usual sign for kinetic energy. Then the spatial derivatives come with a negative sign, but that's fine. And the potential energy term in the Lagrangian always typically comes with a negative sign as well. So the signs are properly defined. When we take the derivative of the Lagrangian with respect to psi comma alpha, we have something quadratic in the psi derivative, so potentially we'll have two contributions. They'll turn out to be the same, but let's work it out. We get minus a half g mu nu. Then we're going to differentiate the quadratic combination here with respect to psi alpha. So the first thing we're going to get is the derivative of psi comma mu with respect to psi comma alpha. And then this comes along for the ride. And the second thing we get is this being left alone, and we get the partial derivative of psi nu with respect to psi comma alpha. So I'm going through all the simple steps here just to illustrate one point. When we talk about those partial derivatives here, we have to treat all the individual derivatives as being independent quantities. So in here, I have all of psi comma t, psi comma x, psi comma y, psi comma z. And here I have all those combinations as well. And these, so all the t, x, y, and z derivatives are all independent in the context of taking those partial derivatives. So when I take a psi comma t and I differentiate with a psi comma t, I get 1. But if I differentiate psi comma t with respect to psi comma x, I get 0, right? So when you take those partial derivatives, you get a Kronecker delta. And same thing over here. And in case you're worried about the index placement here, when you have an index that's lowered in the denominator, it's like it's a high index. It's like it's an upper index. So this is really the definition of a tensor, which is obtained by differentiating the Lagrangian with respect to psi alpha. So anyway, so this is a lowered index in the denominator. It becomes an upper index when you transfer it like that. Okay, so what do you get in the end? Well, you get a minus a half. And now we get two terms. We get the G alpha nu that multiplies d nu alpha, d nu psi. And here we get G mu alpha multiplying d mu psi. And these two things are exactly the same thing. So in the end, we get minus G alpha mu d mu psi. So that's how we take the first partial derivative. We take then the covariant derivative of this. Basically, when you do this calculation, at some point you don't have to worry too much about it, and you sort of learn how to use the rules efficiently. But one thing to be a little bit wary of is that, you know, when we're using mu and nu here, we use them as dummy indices that are summed over. When we're using psi alpha here, we're using alpha as a fixed index that has a specific value. So when you take derivatives like this, you always have to keep in mind what is dummy, what is fixed, and you have to handle these things properly. And if you're in doubt, you can just go through the whole procedure like this. It costs you a couple more lines of algebra, but at least you're on safe grounds. And sometimes these calculations can be a little bit tricky, you know, especially at first when you don't really see your way through it very clearly. So it's worth spending the time just making everything explicit, and then you learn to be comfortable, and you learn to do it very quickly. All right. So this covariant derivative then, well, the covariant derivative doesn't affect the metric. So we end up with G alpha mu covariant derivative with respect to alpha, covariant derivative with respect to psi acting on, with respect to mu acting on psi. And that operator, second order operator acting on psi, is something that would be the curve spacetime generalization of the wave operator in curve spacetime. So that's something I'll often denote box psi. And box is just what you would mean by a wave operator in spacetime. All right. The last thing we have to do is to calculate the derivative of a Lagrangian with respect to psi. Again, psi is treated independently as its derivative, so the kinetic term doesn't enter in this calculation. The only thing that enters is v, so we get minus v prime, where that would denote the derivative of v with respect to psi itself. So v being given some polynomial, typically as a function of psi. And finally, we put it all together. Where's our Euler Lagrange equation? It's up here. So the field equation is going to be this minus that equals 0. So we get minus box psi plus dv d psi equals 0. In other words, our field equation for a scalar field psi is going to be that equation right here. So if we're talking about a free field, if we're talking about a free massless field, v would be 0, and we would be getting the usual wave equation, box psi equals 0. If we're talking about a massive field, free massive field, so for a free massless field, v is 0. For a free massive field, v would be equal to 1/2 m squared psi squared. And that would give rise to the usual Klein-Gordon equation in curve spacetime. So after differentiating, you would get rid of the 1/2. You would get an m squared psi on the right-hand side. And that would be a nice linear equation for the scalar field psi. We call it free because the equation is linear. And then for example, for an interacting field, well, V might still have a mass term, but it might have, for example, a self-interacting term. For example, a psi to the fourth. That's a 4 factorial, but that's not important. A psi to the fourth. That's a typical example of a self-interacting scalar field. And after differentiation, you would get a psi cubed on the right-hand side, and that would be an example of a nonlinear field equation for a scalar field. All right. So that's how we do field theory in curved space-time in a context where we fix the region V in which we work, and on top of that, we fix the metric. The next step is to try to import those ideas to GR and see what needs to be done when you have to vary the metric itself, when the field configuration is given by the metric. So before I move on to that, any questions here? All right. So in the current homework assignment, I'm asking you to go through this procedure for a vector field. So to basically rederive Maxwell's equations in curved space-time from an action principle. So I give you the action, and I'm asking you to go through these procedures to verify that you do get Maxwell's equations as formulated in curved space-time out of it. The only word of caution here is that well, you really have to rethink the whole thing. You really have to go through the entire procedure again because you are dealing with a vector field, not a scalar field. So some of those operations, for example, the switching that I did between partial and covariant derivatives, you have to think very carefully about. You will have to think carefully about in the context of the vector field theory. So my invitation is that, well, take this problem slowly, work it through so that you know exactly how all of this is supposed to be done in the context of the vector field. And then you'll have a pretty good idea of how it's generalized to all other cases when you're dealing also with tensor fields. So my warning is that there's more to that problem that you might think about, and it's not just a problem of substituting the Lagrangian into this recipe. You have to rederive the recipe that's appropriate for a vector field. The issue is that this becomes a vector field, this becomes the derivative of a vector field, so you have to think about how to handle that properly with covariant derivatives. So you have to generalize this to a vector field if you want to apply it to Maxwell. If we want to do it for gravity, of course, we have to generalize all of this to tensors. So that's going to be our next job. So the next job is to introduce a variational principle for GR itself. Let me just write down what the action turns out to be. And then I'll say a few things about it. And then we'll go through the business of taking its variation. So the full action in GR is going to contain a gravity term. And that's going to be a functional of the metric. I'll just write it as G to simplify the notation. And it will also contain a matter part that's going to be a functional of whatever matter fields we might have. Let me call them psi collectively. And the metric also. So the matter action will depend on the metric in addition to depending on the matter fields. The gravitational action, well, you know what it is, right? There's a normalization factor. Again, we're going to be integrating over a fixed domain of our spacetime manifold. The Lagrangian density for GR is well known. It's the Ricci tensor that we integrate covariantly over that fixed region V of the spacetime manifold. But that's not all. There's another term to the gravitational action that's pretty important. That's a boundary term. We didn't have boundary terms in our field theory before. We need one here. The boundary term is going to be a surface integral over our boundary delta V. It's going to care whether the boundary is space-like or time-like, or which portion we're talking about. We'll have typically a time-like portion here and here. We'll have typically space-like portions here and there. So the boundary term will care about whether it's time-like or space-like. The boundary term will involve the trace of the extrinsic curvature on that boundary, and it will be covariantly integrated over that surface. And here I'm using the straightforward integration measure that applies if we're dealing with a time-like surface or a space-like surface. So let me just define my terms. So we're still talking about V. And in V, I'm using space-time coordinates x alpha. On dV, which is the boundary of V, I'm putting in intrinsic coordinates ya, and we're using here all the tools of hypersurfaces. So we have a coordinate system intrinsic to the boundary that is, not directly related to the full space-time coordinates. Epsilon is going to be -1 where dV is space-like. And where dV is space-like, like here, its normal vector is going to be time-like, and epsilon is going to be -1 because epsilon is the norm of the normal vector. And it's going to be +1 where dV is time-like. And when dV is time-like, well, the normal vector is space-like, and its norm then is positive, not negative. There will be transition points, for example, over here, where the boundary turns from being time-like to null, and there's going to be that line, that point here, but if we extend the dimension, it's going to be a line where the boundary is actually null. I don't have to worry about that, because that being a line means that it's really a set of measure 0. When I do the integral, it doesn't contribute anything. The contributions from the integral only comes from, well, basically there's nothing coming here because it's one dimension lower than the full surface integral that we get between here and here. But it does highlight an assumption here that I'm assuming that there's no finite portion of the boundary that's null. I don't want to do that. I'm restricting my dV, so I'm putting a restriction on V such that its boundary only has portions that are null, that are sets of measure 0. So said more simply, the assumption is that dV is almost nowhere null. I know it can be done with null portions. I know we can generalize this for null portions. I know that there's a literature on this somewhere, but I'm not going to include that case right here. That's enough for us to worry about. K, so we have K is the extrinsic curvature on the boundary, so it's defined in the usual way in terms of the covariant derivatives of the normal vector projected down to the surface. So that K is the extrinsic curvature. And K, the scalar K is its trace, defined in this way. And I guess the only other thing I need to specify is that HAB is going to be the induced metric on the boundary, inherited from the space-time metric. And of course, H over here is the determinant. So those are all the definitions. And this, the claim is that this is the full gravitational action. That includes a bulk term and also a boundary term. Before I tell you a little bit more about this, let me just say that the matter action, which is a function of psi and g, well, it's just going to be the usual integral over a Lagrangian density involving psi and its partial derivative. But it involves the metric because we have to integrate this covariantly over that region. So there's an automatic dependence on the metric in the matter functional through the integration measure, but also through the Lagrangian density, because, for example, in the case of the scalar field theory, we had to involve the metric in order to turn those partial derivatives into scalar quantities. So there will be a metric dependence inside the matter action that's, that will be there if you want your matter to couple to gravity at all, right? So that's why it's there. You need a coupling between the matter and gravity, and that coupling has to occur inside the matter action. So how to vary this part with respect to the metric will come to later on, but the harder part of the job is to deal with this gravity action and construct its variation. The variation is going to be subjected to the same sort of rules that we were dealing before, and I'll spell this out in just a second. Well, the main question here is, what motivates this and what requires that? So why a bulk term? Why a boundary term? Well, the motivation for this is pretty clear, right? So you need the Lagrangian density for gravity to be a proper scalar quantity. You would like this scalar quantity to be more or less along the lines of what we had for the Lagrangian. You would like the Lagrangian density for gravity to involve the metric, obviously, and to involve its first derivatives. And you would like very much that Lagrangian density to only involve the metric and its first derivatives in a properly scalar way. And it just can't be done. The point is that the first derivative of a metric will never be a tensorial quantity, right? The first derivative of a metric is equivalent to a Christoffel symbol, and you know that the Christoffel symbol is not a tensor. And therefore, there's no way that you can really combine Christoffel symbols or first derivatives of metrics in a way that combines into a scalar that would be a good candidate for a gravity action, for a gravity Lagrangian. So if you insist that you want a scalar, and we will, then you have to turn to second derivatives. You have to involve second derivatives of the metric. And now you have a Lagrangian density that can depend on metric, first derivative, and second derivative. And now you have the freedom of packaging all of this into a properly scalar quantity. And the simplest thing you can think of is the Ricci tensor. That's really the simplest combination of these ingredients that gives you a properly scalar quantity to build a candidate action for gravity. You can do more complicated things. You can add all sorts of higher order terms. For example, you can take the Riemann tensor, you can square it, you can put it in, and that's a proper tensorial quantity. You could take the Ricci tensor, you could square it and put that in. That's also, a properly scalar quantity. So you can do more complicated things. They would all complicate the picture quite a bit. They would all give rise to theories that are not Einstein's. So a characteristic of Einstein's theory in this context is that it's really this, the theory that results from the simplest action you can write down. That is a properly tensorial quantity involving the smallest number of ingredients that you can involve, and that's the metric, its first derivative, and its second derivative. But now something has changed. In the scalar case, we insisted all along that our Lagrangian was supposed to depend only on the field and its first derivative. We never said anything about second derivatives. We could generalize it, right? We could invent a field theory that would have second derivatives inside the Lagrangian, and we could modify the variation of the action to include, an additional term up here that would come from the variation of the second derivatives. We could do all of this, no problem. But what we would have as a result would be a field theory that involves not second order differential equations for the field. Now we would have third order differential equations. because you see how it went, right? In the process of this calculation, we turn a Lagrangian that depends on first derivatives into something that produces second derivatives. If we had, second derivatives, in fact, it would get even worse. We would have third and fourth derivatives coming out of this procedure. Einstein was very clear all along. He wanted a field theory for gravity that only involved second derivatives because he wanted something that was as closely analogous to Newtonian gravity as he could imagine. So here we have a strange situation where we have a Lagrangian density that requires second derivatives. But in the end, we're going to come out with Einstein's theory. And the field equations that emerge from this will be second order. It's almost too good to be true. Something magical occurs, and something magical almost occurs, but it doesn't occur unless you have the boundary term there. We're going to see that in great detail when we go through the procedure. But the bottom line is this: the hint of this is this. Suppose we went back to scalar field theory and had second derivatives term in the Lagrangian density. Maybe we would have to rethink this. So here we had a variation rule that restricted the field variation to be 0 on the boundary, but we never said anything about the variation of the field derivative. If we were to introduce additional derivatives in the Lagrangian density, maybe we would be in trouble when we do the variations. Maybe we would end up with additional boundary terms that would require possibly additional rules, like a condition that not only the field itself doesn't vary on the boundary, but that its derivative also doesn't vary on the boundary. I don't know. I haven't carried out the exercise to see what happens. But the problem that arises in gravity is that if you proceed on the basis of the bulk action alone, because the Ricci tensor has second derivatives terms in it, when you go through the variation and you want to set it equal to 0, if you didn't have an extra term on the boundary, you would find that it's not enough to impose the variation of the metric being 0 on the boundary. You would have to impose also that its first derivative vanishes. And that's too much. Too many conditions. We don't want to impose that much. It's one thing to say that the variation of the field vanishes. That's something that is well understood and well within the formulation of field theory. To start imposing additional conditions would not be justified, would not be motivated, and would require basically a departure from the usual rules of variation in the context of field theory. So the reason for the boundary term is that, in fact, it's there to compensate for the extra mess that arises because of those extra derivatives. When we vary the action, we're going to see that imposing 0 variation for the metric allows us to get most of what we want from this, but there would be residual terms that would require additional derivatives to have no variation as well. By including the boundary term, we fix that. So the boundary term is absolutely crucial in order to fit this within the usual rules of field variations and action principles for field theories. If you didn't have that, you would have to change the rules. You would have to impose too many conditions, and it's not clear that the whole thing would be self-consistent. So we're going to see that. We're going to start with this. We're going to vary that. We're going to see where we go with this, and we're going to see that the usual rules would not quite work, and if we want them to work, we have to modify the action. So in the old days, in the old textbooks on GR, typically you will see the bulk term written out as the usual action principle for gravity. That's an action principle that in fact goes back to Hilbert. It's usually called the Hilbert-Einstein action. That's very famous, and all the older textbooks basically talk about that and only talk about that. It's only fairly recently, in fact, it goes back to the 70s, where people started to understand the role of the boundary term. And in fact, there's more to be said about the boundary term. This is not even the final word on that. There's more refinement that's going to be coming down the line. We'll talk about that this afternoon. But it's only in the 70s that the role of the boundary term became better understood. And even that, if you look at most textbooks out there, the story doesn't seem to have caught on in a lot of the textbooks. And it's still an issue that tends to be not discussed or ignored or barely mentioned. So, but it's actually very important. I think to have a well-defined action principle for GR, you cannot ignore the boundary term. And if you do anything like semi-classical calculations involving gravity, for example, tunneling processes, anything like this, the classical action is very important. The numerical value of the action turns out to be very important because you can approximate, in these types of situations, you can approximate a path integral by, so a path integral involving, an integration over metrics times e to the I action for gravity. Sometimes in quantum gravity type processes, you would end up evaluating a path integral like this. And if you calculate the tunneling process, you would calculate the path integral associated with the tunneling. This is often well approximated by just taking the classical action. You work in the Euclidean sector, so you get rid of minus I, and you have an I. So this is an Euclidean calculation. But you can approximate the whole path integral by evaluating the classical action and putting that into the exponential factor. And typically, you get good results for tunneling processes, tunneling probabilities, by doing what is called a semi-classical evaluation of a path integral. Well, if you're going to do that, you have to be clear on what the definition is for your action, because its numerical value is going to be telling you something physically important, like probabilities. If you get the action wrong, you'll get your values wrong. So the presence or not presence of a boundary term is very crucial, because this will, in fact, alter the numerical value for the action. So it's important for that, in addition to being important just for self-consistency of the whole field theoretical approach to GR. So bottom line is that we really need to worry about this. It's very important. And in fact, it's present in the literature, but not so much present in textbooks for reasons I don't quite understand, except for the fact that it requires a little bit more calculation to handle this, as opposed to what you have to do when you only have to worry about the bulk term. Any questions? Okay, so let me go ahead then and start calculating the variation of that thing. Okay. Let me spell out the variation rules. So, as with the scalar case, we're going to be saying that the variation of the metric is going to be arbitrary everywhere in V, but 0 on the boundary. And this is the only condition I wish to impose. I don't want to make any statement about how derivatives will vary. A consequence of this is that the induced metric on the boundary only involves the metric on the boundary. And if there's no variation of this on the boundary, there will be no variation of that on the boundary. Right? So an immediate consequence is that if I fix the metric on the boundary, I fix not only the space-time metric on the boundary, I also fix the intrinsic metric on the boundary. So there is no variation of the induced metric on V. Well, I don't need to say on V, because the induced metric is defined only on V. So that's something we can keep in mind. Another consequence of this is that even though I don't want to make any statements about derivatives, if the metric is fixed on the boundary, all tangential derivatives on the boundary will be fixed as well. Right? So if the metric doesn't change as I move, what I mean to say is that the metric is fixed everywhere here, which means that derivatives of the metric within the boundary has to be fixed as well. So what I'm really trying to say is that if I take a variation of the metric and I calculate its tangential derivatives, this has to vanish. Because this derivative, so what I really mean by that, so I should write it out in a simpler form. What I'm really saying is that I take the metric derivative, I take the metric variation and I differentiate it in the direction tangent to the boundary. And because this is 0 on the boundary, the derivatives have to vanish also, provided that I'm differentiating on the boundary. What's not true is that the normal derivatives will vanish. Because the normal derivatives will probe what happens when I go a little bit off the boundary, both in and out. So if I take a derivative in that direction, well, I know that the metric doesn't change if I'm on the boundary, but it does change if I go off the boundary, inside the boundary. And I cannot say anything about the way that those derivatives behave. So basically, I can assume that all tangential derivatives vanish because of this condition, but I cannot say anything about the normal derivatives. Right. So that's something to keep in mind as well. Another thing when we do the variation, typically it's useful, it's convenient. Instead of using the metric itself as the thing to vary, we're going to vary the inverse metric. So if I know the metric, I know the inverse metric. So if I vary the metric, I can get to that by varying the inverse metric. It's just a bit more convenient to do it. So instead of those variations, we will work with these guys. So the variation of the inverse components of the metric. And clearly, these things are not independent, because the inverse metric is directly related to the metric. In fact, I can work out a relationship. I can start with this defining relation here for, that's not what I wanted. The definition of the inverse metric is to say that its product with the actual metric is the identity matrix. I can take a variation of this. So I'll get this on the left-hand side plus this on the left-hand side. All of that being equal to 0. And that tells me that I can solve for this given that by just rearranging the indices a little bit. So if I multiply this by let's see, what do I want to do? I want to multiply this by G alpha gamma, G beta, no. Yeah, so let me multiply this by G alpha. What do I want to do? Yeah, delta G beta gamma, delta G alpha beta, plus G alpha. So if I multiply G alpha beta by G alpha delta, I get delta beta delta. That's still equal to 0. And by just redefining my indices, I get that the variation of the metric itself, beta delta, is minus the variation of the inverse metric and raising and lowering, lowering all the indices. So basically, we can work with this And it's, formally the same thing as dealing with these guys. I can get these guys from these guys, but it's more convenient for us to do the variation, to deal with the variation of the inverted quantities, not the metric itself. Right? So we're going to be working with these guys over here, so that will simplify the calculations. Another useful relationship that we're going to need is what happens to the metric determinant if I vary each element of the metric itself. And the rule for that goes back to the rule we talked about a long time ago when we were differentiating the metric determinant with respect to space-time coordinates. So if you differentiate the metric determinant, it changes because each element of the metric itself changes. So the changes in the metric elements propagate into a change for the metric determinant itself. So if it's true for coordinate derivatives, it's going to be true also for variations of the type we're doing here. And I don't want to mess up my minus sign here. If you go back to this part of the course and chapter 1 in the book, the rule for this is that the change in the metric determinant is going to be related to the change in the inverse metric in this way. And again, that's basically the same rule that we had before to relate the derivatives of the metric to derivatives of the determinant. The only change here is that instead of talking about the change in the metric itself, I'm using my rule, I'm using my convention that I'm going to be relating everything to the variation in the inverse metric. Okay, one more thing before we move on. We know that the Christoffel symbol is not a tensor. But something I didn't talk much about, but something that was stated again in chapter 1 of the book, is that even though so what we're doing here is so we have the initial set of Christoffel symbol that's related to or compatible to the original metric, the one about which we're about to take a variation. When we vary this, we end up, delta G, we end up calculating a Christoffel connection that's going to be compatible with a different metric. And that's going to be equal to the old connection plus a variation in the connection. And we're going to work this out at some point. The point is that the variation is, I'll just write it systematically, the variation in the connection, obviously, is a difference between two connections. One compatible with this metric, the other one compatible with a different metric. And even though the Christoffel symbols, each one here is not a tensor, the difference between two Christoffel connections, the difference between two connections is a tensor. So the Christoffel symbol itself is not a tensor, but its variation is a tensor, and that's something we can use to our advantage in simplifying the calculation. So the proof of this has to do with the fact that when you consider coordinate transformations, you find that the way that things transform under coordinate transformations, when you look at how the Christoffel symbols transform under a coordinate transformation, you find that they're the usual partial derivatives multiplying the old connection. And if that was it, we would conclude that this is a tensorial transformation. But in fact, it's not it. There's second derivative terms that occur here all by themselves. So there are additional terms that arise when you see what's going on with coordinate transformations of Christoffel symbols. And this additional term here basically prevents the whole thing from being a tensorial transformation. But if you take the difference between two connections, when you look at its transformation property, you'll end up taking this equation and subtracting something else, right? If you have this connection and you have another connection, this one will be given by a similar transformation law. But when you take the difference, which is, gamma minus gamma bar, what you find is that when you take the transformation, you kill these terms because these terms don't involve any gammas. So when you take the difference, these terms cancel out. The only thing that survives are going to be the usual partial derivative terms, and that describes the tensorial transformation law. So that's how you can prove. There are other ways to prove it, but basically that's how you prove that differences in Christoffel symbols form a tensorial quantity. Okay, I think with all these rules, we're free to go. And yeah, I will get started on this, and then I'll finish the calculation this afternoon. So any questions or any mysterious aspects here before we move on? Okay, well, let's just get going. So what I'm going to do is to start with the bulk term. For the time being, I'll pretend that this doesn't exist, and I'll just proceed with the bulk term, and then we'll see along the way that, well, we need to reinsert it in order to have a well-defined variational principle. So let's take our bulk term, and I'll forget about the 1 over 16 pi. That just comes along for the ride. We'll reintroduce it later on. So let's do a variation of this over here, which means that I consider two configurations with two different metrics, and I subtract one from the other. So what do we mean by that? Well, we consider the variation of, so what's the Ricci scalar? The Ricci scalar is, well, the Ricci tensor, and we multiply the metric, the inverse metric, we multiply the metric determinant, and we integrate. So when I do the variation, everything changes except which domain of integration we work with, right? So the domain in space-time is not changing. The volume V is fixed. So everything else changes. The Ricci tensor certainly will change. The inverse metric, of course, changes. The metric determinant will change. So everything inside the integral is subject to variation, but not the integration domain itself. So let's just do it all. So we have an integration over V. The first thing we have is the variation of the Ricci tensor all by itself. Then we leave the Ricci tensor alone, and we have the variation of the metric. And then we have the variation of the square root of G, and I'll just write it out for what it is. I'll just use this expression up here, is just minus a half root G, G alpha beta, variation in G, times the Ricci tensor, which is still coming along for the ride. So that's what we get for the variation of the integral. Let me just regroup a couple of terms here. We have the first integral, which involves the variation of the Ricci tensor. And then we have a second integral that involves the Ricci scalar minus half the Ricci scalar, sorry, the Ricci tensor minus half the Ricci scalar. Yeah, you're right. Yeah, that's right. So I confused I have too many alphas and betas, so that's always a warning sign when you do calculation. And you have too many of the same indices, that means something has gone wrong. So over here, right, so I was doing the variation of root G. So instead of alpha beta, I should have used mu nu delta G mu nu. and I still had the remaining G alpha beta and the remaining Ricci tensor. So that's what I should have had. And then this and that gives me the Ricci scalar. This I can rewrite as G alpha beta. Now I can do it. All of this multiplies the variation in G, and all of this I integrate over root G d4x. So it looks like we're on the right track. It looks like we're having exactly what we want to have on the right-hand side, right? We have our Einstein tensor coming out of this very easily just by varying inside the integral what comes from this and what comes from that. But we still have to worry about this first integral that comes from the variation of the Ricci tensor with respect to the metric. So we'll have to do quite a bit of work in order to deal with that first term. But obviously, what we need to, what we want to have here is that first term giving us nothing in the end. And what we want from all of this is basically something that involves the Einstein tensor inside the integral. So it turns out that, well, this will happen, but we'll have to work quite a bit in order to make it happen. And that work will involve reintroducing this boundary term. So let me just do a little bit more to get started with this calculation right here. I'll leave this here. Okay, so now we have to calculate the variation of the Ricci scalar, the Ricci tensor. And obviously, if I vary the metric, everything will change. The Riemann tensor will change. The connection changes, as we talked about. And therefore, the Ricci tensor itself will change. And you can imagine that this is a pretty horrible calculation to do, to calculate the variation in the Ricci tensor, because the Ricci tensor has, yes, a relation with the metric, but it's all very, involved, right? So we have to go back to all of this. Well, it turns out that there's a hard way to do this calculation, and then there's an enlightened way of doing this calculation. So I think I'll do the enlightened way. I guess you won't object, right? The easy way to do the calculation, and it's often true, is to just momentarily work in a coordinate system that turns out to be convenient. So what we're going to do to calculate this variation, we're going to be working in a local Lorentz frame at some point P. So what I mean by that is that we're going to be working at P where the connection associated with the background metric, the one from which we vary, is going to be 0 at P. So we're going to set the connection terms to 0. That's going to simplify things tremendously. But we have to be very careful with that. What we cannot say is that the derivatives of the original connection are 0. They're not. We can set the connection equal to 0. We can set the metric, for that matter, equal to the Minkowski metric in this coordinate system. But we cannot set the derivatives of the connection equal to 0. Another thing we cannot do is to declare that the variation in the connection is 0. It's not 0. The original connection associated with the background metric is 0. But this is a connection that refers to a varied metric. and that's not going to be 0. But if we proceed along those lines, if we use this simplification, then everything does simplify quite a bit. So, for example, well, what's the Ricci scalar? What's the Ricci tensor? The Ricci tensor, schematically, is going to be a term involving partial derivatives of connections plus terms involving the square of the connection. Right? So before putting in indices, I just illustrate the structure of the calculation. If we take a variation of the Ricci tensor, what we'll get is a derivative of a varied connection minus a derivative of a varied connection plus twice a connection times its variation minus twice a connection times its variation. And the point is that we're working at P where this can be equal to 0, can be set equal to 0. We cannot set either one of those two things equal to 0. Right? So we have to deal with these because those involve derivatives of varied connections, so we have to deal with that. But nevertheless, that's still a big simplification with respect to what we would have to do if we had to carry all the extra terms as well. So more fully, if I put it back indices, so now all you have to do is to look up the definition of the Ricci tensor in terms of the connection that you get by looking up the definition from the Riemann tensor and taking the appropriate contraction. What you find is that in this coordinate system where gamma is equal to 0, this is equal to the derivative of the varied connection with those indices and this derivative of the varied connection with those indices. And now we do the magic thing where we turn this into a properly tensorial equation by replacing this partial derivative and this one by covariant derivatives. Covariant derivatives defined with respect to the background metric. Now, with no restriction on the equal sign, with no restriction on the coordinate system, I claim that this is exactly the same thing as this. Which is a properly tensorial equation. So the argument is always the same, right? Because the connection is 0 at P, we have equality in that coordinate system between the partial derivative and a covariant derivative. The difference would involve a bunch of gamma terms that all are 0 in that coordinate system. So I can change in this coordinate system this partial derivative by a covariant derivative. I can do the same thing here and here. But once it's written in this form, I look at the left-hand side and I see it's a perfectly fine tensor. I look on the right-hand side and I see that it's also a perfectly fine tensor because this by itself is a tensor and I'm taking a covariant derivative. This is a tensor and I'm taking a covariant derivative, and therefore the right-hand side is a tensor. I have equality of those tensors in the original coordinate system, but that guarantees equality in all coordinate systems. So at this stage, I don't need to refer to the special coordinates anymore. I have a perfectly fine tensorial equation. Now, you can rederive this the long way, if you wish, by keeping track of all the Christoffel terms. You will end up back there, obviously, but this saves you a lot more algebra, and it's often a trick that's worth using. It saves you a lot of work, and potentially it saves you from a lot of mistakes because you don't have to carry all those extra terms that would be heavy to carry for a calculation like this. All right, so I'm going to stop here. So that's the variation of the Ricci tensor in terms of the variation of the connection. The next step is to relate the variation of the connection to the variation of the metric, and after that we can put it all together and look at that Riemann term, Ricci term in the in the bulk integral. Any questions before we quit? So these calculations are a bit, involved. We have to go through them. I think it's a useful exercise to go through them. But, it is a bit involved and not pleasant for anybody, but, sometimes we just have to do things like that. Okay, so I'll see you in the afternoon.